Anirudhan, yesterday we discussed about a voltage source and a resistor in parallel, and we found out the current through the resistor and so on. But most of the circuits I see has got many components. For example, Janagiraman was explaining millions of transistors in a IC and so on. So can I just use this Ohm's law and find out current in those circuits?
So you have to go a little bit beyond Ohm's law. There are very classic ways of solving more complicated circuits. So we can see that today.
Because there are some systematic ways.
There are some systematic ways of doing this.
Sure.
So what we will do, we will start with a slightly more complicated version of yesterday's example. Actually, why don't you suggest some circuit?
Maybe
I'll start drawing. I'll start with the voltage source.
Sure.
You tell me what to. So we know what series and shunt means. So you tell me whether to add a resistor in series or shunt, and I'll keep doing that. So I am going to first draw my voltage source. So I'll say voltage source V. So now you have to tell me what to do.
We will add a resistor in series.
Resistor in series. Okay.
Maybe one resistor downwards.
One resistor shunt. Okay.
Yeah.
Okay.
And then connect back to the voltage.
Connect back to the voltage source. Okay. That is it.
I would add one more resistor.
Oh, you're making it quite complicated now.
Little
bit more complicated. Okay. Okay. And then what else?
And connect back to
back. Okay. You will do. Okay.
Yeah.
Okay. So this is simple enough such that we can show everyone the systematic way of solving it. So shall I name these resistors?
That will be good.
So I will call them R1, R2 and R3.
Yeah.
So we want to find out systematically what the voltages and currents in this circuit are.
Okay.
So in fact, that is if you want to analyze an electrical network, what that means is that you need to know the voltage across every element and current through every element.
Yes.
So these two things you need to know, because at the end of the day, the electrical quantities are voltages and currents.
Yes.
So now, for example, for the voltage source, we already know what the voltage is, that is V.
Yes.
But we don't know the current through that voltage source.
True.
Yesterday, actually, when we only had one resistor, it was very simple. The current through the voltage source was the same as the current through the resistor. But now this is more complicated. So in fact, there are two different ways of solving this network, systematic solving of networks.
Okay.
We will start with the first one, maybe slightly easier to understand. So what I'm going to do, in this method, this is called nodal analysis.
Nodal analysis.
Nodal analysis.
So it has something to do with the nodes of the circuit?
Yes, of course. So in fact, I can already imagine your next question. You're going to ask, what is a node?
Yeah.
A node is a point where more than two components meet.
Okay.
We are talking about two-terminal electrical components.
Okay.
Any point where more than two nodes meet is technically a node. Now, this is also a node. Even when two things meet, it is also a node. So, for the purposes of this discussion, we will also call that a node.
Okay.
So, we will call this node 1. We are going to number it. We will call this node 2.
Okay.
Because next question is, even this point where it turns can also be a node and so on. I don't want to this thing, but there is a third node as well.
Okay.
So this is third node, but normally for nodal analysis, what we will do is we will take one node as a reference point.
Okay.
So in fact, I am going to call this node 0. Node 0. Okay. So now at nodes 1 and 2, we are going to do something special. So if you take any electrical network, the first thing before you do analysis, you have to make some certain assumptions.
Correct.
Now, one of the assumptions we are going to make is that the voltage at that node is not increasing or decreasing.
Okay. For a given circuit.
For a given circuit.
Like this.
Like this. So, in other words, I am going to assume, so now you remember in yesterday's class we talked about an electric field and charges and so on.
Yes.
So what happens is we saw that there were higher potential nodes and lower potential nodes. and if your potential increases at a particular point, that means that more charge is being added, more positive charge is being added.
Yes.
If the potential decreases, charge is being removed.
Yes.
So our assumption is potential is staying the same.
So the charge is constant.
The charge is constant.
Mhm.
We are assuming that the charge at node 2, so there is no net charge which is being pushed into node 2.
Mhm.
There is no net charge which is being pulled out of node 2.
Means some charge is coming, same amount is leaving.
Correct.
Okay.
Because now we are talking about a circuit where current is flowing.
Correct. Correct.
So these charges are not static, but the amount of charges moving in has to be equal to the amount of charges moving out.
Understood.
What does that mean in terms of currents? Automatically, which means that the amount, because after all, we said yesterday current is nothing but
dq by
dq by dt.
Yes.
So which means if amount of charge flowing in is the same as amount of charge flowing out, amount of current flowing in also has to be the same as
Okay.
total current flowing out. So in fact, we are going to use that systematically in nodal analysis.
Great.
So what I am going to do is I am now going to represent the current through each element.
Okay.
So let us say the current through resistor R1 is I1. The current through, okay, so let me, are you comfortable with this direction of I1 or would you like a different direction? This method works independent of which direction you choose.
Sure. Sure.
You are happy with this direction?
So if you are going to analyze, let's say node 2,
yes.
for me maybe it's easy if current is leaving from all those nodes.
Okay. So then what I will do, I will choose the directions like this.
Yeah.
And then which means for R2, I am going to choose the current I2 like this. And I am going to choose the current I3 through R3 like this.
Okay.
Now, so what did we say? We said sum of all currents leaving the node should be equal to sum of all currents entering the node.
Okay.
In fact, the way you have chosen the directions,
all currents are leaving.
all currents are leaving, which means this is 0. There is no current entering it.
Yeah.
In fact, the total current leaving is I1 plus I2 plus I3. So we have current I1 leaving through R1, we have current I2 leaving through R2, and we have current I3 leaving through R3.
Yes.
And there is no other current entering it.
Correct.
So the way you have chosen it, the sum of all these currents is 0.
Yeah.
Now what about the voltage source V? We actually, because we said that I is also a node, we also have to choose a current direction for that. Which current direction would you like to choose for the voltage source? Normally,
current comes out of the
positive node. That is our normal convention. So we will choose that. So we will say that this current is actually I am going to call it IV.
Okay.
Okay. Now you can do, because we have chosen I1 also to be a node, we can do nodal analysis at node 1 as well.
Okay.
So I will say this is at node 2. So at node 2. At 1 also we can do it. What is the total current leaving? The total current leaving is actually 0 in that case. And the current entering the node is actually I1 plus IV.
Yeah.
So what you can see is that at node 1, so this is at node 1, actually what this means is that IV is nothing but minus negative value of I1.
Correct.
And I think anybody who looks at the circuit, it's obvious.
Yes.
Right? So what you are saying is that, the positive end of the voltage source is just connected to the resistor.
Yeah.
So obviously the current has to enter the resistor from the voltage source.
Yes.
So all we are saying is that IV is minus I1. So which is why normally this kind of node, you don't explicitly call it a node.
Yeah.
It is after all only two elements connected together.
Correct.
So you don't need to represent it as a node.
Yeah.
So now, as you can see now, this just tells you that the current through the voltage source is minus I1. We know that. Actually, it would have been obvious to anybody because this current would have just flown through the voltage source. This equation is now important. So we are going to take that equation and work on it a little bit further.
Okay.
So I'm going to write it separately here.
Okay.
So I'll call it I1 plus I2 plus I3 is 0 is what we wrote.
Correct.
Now what I'm going to do, I don't know what I1 is, I don't know what I2 is, I don't know what I3 is. What I'm going to do is I am now going to use Ohm's law.
Okay.
You are saying whether we could use Ohm's law to solve the circuit.
Yeah.
We have to use Ohm's law
Okay.
to solve the circuit, but we need something more, which is this. I1 plus I2 plus I3 is equal to 0. Now what I can do, I can write I1 in terms of the different voltages.
Okay.
So the next step in doing nodal analysis is to denote the voltage at each node
Okay.
by some variable.
Okay. So you are going to give some voltage variable to each node.
Each node.
Oh,
So-
then we can use.
Then we
Ohm's
can
law.
use Ohm's
Yeah,
law.
Yeah.
So now I am going to call this V1. At node 2, I am going to call this voltage V2.
E2.
And because this is the reference node, we'll
Zero.
just call it 0. Because yesterday we talked about potential difference. We didn't say potential. So you take any one node as reference, that is 0 for this calculation. You are calculating the voltage of every other node with respect to this. You can also choose this as 0 if you want. That is commonly not done.
But this
you
will
can
be
choose.
easy to.
This is easy to
Yes.
write. Now what is I1 using Ohm's law?
V2 minus V1 by R1.
V2 minus V1 by R1. So I1 is V2 minus V1 by R1. I2
V2 by R3.
is simply V2 minus 0 by R2,
Yeah.
which is just V2 by R2.
Yeah.
And I3 is again simply V2 minus 0 by R3, which is just V2 by R3. So now all you have to do is take these three equations
Sum it.
and sum it and set it to 0.
Equate to 0.
So you are basically going to put them back into this. So I'll do that on the next page.
Yeah.
So what I will do, so again, so I1,
Or V2 minus V1.
yes, so I thought I will write the equation again. So maybe we can just directly write it, you are
Yeah.
right. We will save a step. So we said V2 minus V1 by R1 plus
V2 by
V2
R2.
by R2, correct. And what is the third
V2
term?
by R3.
V2 by R3. This is 0.
Yeah. For the other node.
For the other node also we have to write. So now what do we do for the other node? So let's go back. We said this voltage at V1,
It's already known. No?
it's already known actually.
Mhm.
That is nothing but V.
Mhm.
So we can just go and say the
V1 is V.
V1 is nothing but V. So
Okay.
we don't need to write any Ohm's law. We already know V1. So now all we have to do is go back and
Substitute there.
substitute here. So substitute this here, and what you find is V by R1. So I am going to move that V1 term to the right hand side
Yes.
because we already know this. Okay, what I will do, I will write it like this. V2, we'll keep the V2 terms on the left hand side and move the V term to the right hand side. So V2 by R1 plus V2 by R2 plus V2 by R3 is nothing but V1 by R1, which is V by R1.
Yeah.
So now we know the voltage at V1 and V2 because now you can see. So V2 into 1 by R1 plus 1 by R2 plus 1 by R3 is nothing but V by R1. Now you can see you can very easily solve this. So we have managed to solve V2. We have managed to solve V1. Now the minute you know V1 and V2, you can also solve for I1,
Yeah.
I2 and I3.
Obvious. Yeah.
Now you know everything about the circuit.
So this way, even if the circuit is a little bit more, I can assign nodes,
Correct.
write these kind of equations, solve.
Perfect. You can now do this for, you can now,
cool.
yes, you can do this for any complexity. Your circuit can be as large as you want. You can do this solving. Now, it is easy when the circuit is small to do it by hand.
Mm-hmm.
Now, the minute it becomes a little bit more complicated, we will maybe when you have more than 2 nodes, we will do it in a later class.
Sure.
We will we will write down, equation writing is similar, but what we will do is we will use a different mathematical technique to solve it. And then once you go beyond a certain point, you have to use computers in today's day.
Yes.
In fact, you are talking about very complicated circuits
Millions.
with millions.
Yes.
You will have to solve it using computers. There is no way nobody is going to sit down and be able to do it by hand. So what we will do, you will follow this exact same procedure and you can solve for the voltages and currents. Now this technique, as I said, is called nodal analysis. Now this particular equation here is very important. That is where we started.
Correct.
That is actually the core of this idea. So very, very important idea. In fact, in electrical engineering, it is not just an idea, it is a law. It is a law.
Okay.
It is a law named after the scientist who discovered it. So the scientist was a German scientist. His name was Kirchhoff. So we call it Kirchhoff's Kirchhoff's current law. Sorry, current law.
In short form,
take a guess.
KCL.
KCL. Perfect. You would just call it KCL. So you would hear electrical engineers, circuit designers saying KCL, you will know what it means. So this is Kirchhoff's current law. So sum of all currents leaving the node has to be equal to sum of all currents entering the node. And this is a really important law in electrical engineering, in electronics engineering.